So we'll continue this chapter by looking at a simulation. It's called a Phet, physics. I don't remember what Phet stands for, but it's something from Colorado.edu. And if you ever want to run any of these simulations, you can just go to phet.colorado.edu, and there's all kinds of great simulations to play with that allow you to understand some tough physics concepts or some easy physics concepts. So here's the Phet simulation. And remember, this was observed by Hertz, and classically, not really a problem in terms of what's going on. So I can so there's a light source here, and I've got an evacuated glass cylinder with some metal plates, a cathode and an anode, and there is the potential of, that was not a pun, but a potential of putting a potential, a battery here that can be turned on, or a power supply that can be, a voltage that can be turned on. But forget the voltage for now. There is no voltage, zero voltage. Here's the photoelectric effect as observed by Hertz. Let's turn up the intensity of the lamp. Look what happens. If I turn up the intensity of the lamp, electrons are emitted. Now, of course, we don't see electrons. What you actually see is a current in this circuit, because as you turn up the light is shining on the surface is then emitting electrons. Those electrons go across the vacuum, and they then go through the circuit and create a current. So what you actually measure is a current, right? These are just cathode rays, which are indeed electrons. So classically, there's not a problem with this observation. It's the measurements that don't make sense classically. Remember, these experiments that we're talking about maybe were experiments that were understood empirically but couldn't be explained. And so some scientists had to come along and really, dig deep and come up with a new theory in order to explain them. So the photoelectric effect, Einstein was able to explain it using quantization of energy. We'll get there. Black body radiation. The experiment is looking at the emission of a body, which anybody can do, and we can empirically describe it. But in order to explain it, Planck had to come along and talk about quantized oscillators. So there's the experiment, there's the result, there's what wasn't understood about the result, and then there's the explanation. Those you should understand each piece of that for atomic spectra, for the black body radiation, for the photoelectric effect, and for the other pieces that build up to quantum mechanics. So anyway, coming back to photoelectric effect. So here's what's not understood. Think about classically what's going on. Classically, if you're shining light, which you have a sense that light has energy, you're shining light on a surface, and that surface is emitting electrons. It's because the energy of the light is being absorbed by the metal, and it is giving the electrons extra energy, so they escape from the metal, and hence these electrons are getting energy. So you would think that if you increase the intensity, you're going to increase the current, and indeed I do. So that's classically reasonably reasonable, at least qualitatively reasonable. Increase the intensity, I increase the current. But here's the problem. I can now take, I was messing with something, so you can see some of these electrons are not going anywhere. I can now take this voltage down here, and I can turn it on. And watch what happens if I turn on the voltage, right? Voltage will also help to accelerate those electrons. So if I turn up a voltage pushing the electrons in this direction, they're negative, which is why the battery would have a current going this direction, therefore pushing the electrons in that direction. Pushing the electrons, they're going faster. Now what happens is if I turn it the other way, what happens is I can actually slow down the electrons, and I can turn this voltage up in the negative direction, so much so that no electrons ever make it to the other plate. The current is zero. So if I want to measure the energy of these electrons, this is a very easy way to measure the energy of the electrons. Now I have, by turning up the voltage until the current goes to zero, I have now measured the energy of the electrons. The energy of these electrons must be 1.2 electron volts, because that is the energy it took. Well, let's see. Is that the energy it took to stop them? Yeah. Are they going to make it? Are they going to make it? Are they going to make it? Oh, no, they're not going to make it. Maybe it's 0.8 electron volts, because that's the energy it took to stop them. 0.8 electron volts. So that's the amount of energy that approximately that the electrons have. All right, let me turn it down just a little. 0.6. Yeah, there you go. Now you get a current. Okay, turn it back up to 0.8. Turn it back up to 0.8. Here we can just type in 0.8. Okay. So now at 0.8. Oh wait, there's still some current. Okay, are they stopping? Yeah, they're stopping. Okay. So now classically, what should I be able to do? Leave the voltage. This is called the stopping voltage. This is called the stopping voltage. Let's leave the stopping voltage at 0.8. And if I want to give the electrons more energy so they make it across, what do I have to do? Classically, you would say turn up the light. Turn up the intensity of the light. So watch what happens if I turn up the intensity of the light. Turn up the intensity of the light. Turn up the intensity of the light. I'm turning up the intensity of the light. Do you see what happens? When I turn up the intensity of the light, the electrons are not making it across. It hasn't changed the ability of the electrons to get across. And you would say, but I'm turning up the intensity of the light. I'm giving the electrons more energy. And it turns out we aren't. By turning up the intensity of the light, we are not giving electrons more energy. But something did change. Did you notice what changed? Let's go ahead and turn down the intensity of the light and see what happens. Turn down the intensity of the light. What happens when I turn the intensity way down? The electrons still have the same amount of energy. In other words, they're going just as far as they were before, but what's changed? Hopefully you can see that what's changed is there are fewer of them. There are fewer electrons, so turn down the intensity of light even more, and there's fewer electrons. Look at that. There's only a couple now, but they are going, well, are they going as far? Yeah, they're going as far. On average, they're going as far. They're just not making it across. So the intensity changes the number of electrons that are being emitted, but it doesn't change the energy of the electrons being emitted. And classically, we would think that the intensity would give the electrons more energy. But there is something that we can change that will give the electrons more energy, and this is not explained classically in any way whatsoever, and that is the color of the light. If I turn up the color of the light, turn it up, meaning go to the more energetic light, which is UV. I said energetic. That's a quantum mechanical effect. Turn up the bluer light, UV. Right, go to more blue light, and watch what happens. We've got a current now. So the blue light gives the bluer, or the more UV, towards the blue end of the visible spectrum, gives the electrons more energy. What happens when I turn the light down to red, the other end of the spectrum? Look what happens. When I turn it down to red, oh wait, they stop coming off altogether. Turn up the intensity. Whoops, let's turn up the intensity. Whoops, let's turn up the intensity of the red light. I have no electrons. So it turns out that the energy of the electrons being emitted is dependent on not the intensity of the light, but is dependent on the color of the light. And that is definitely not a classical thing. And that is what Einstein had to describe with quantum mechanics in order to explain what's going on. If I turn the light, go to the bluer end, I get more energetic electrons. Go to the redder end, I get less energetic electrons. So let's go ahead and put this down on paper.